Great. So this is going to be a talk about some work with Gautam, actually, as well as my excellent students, Changhan Chen and Elisa Tabor. It is very much work in progress, as somewhat evidenced by the fact that Gautam did not know the title of what I decided to call it. Great. So I want to talk a bit about flat space, what it might mean to have some notion of holography in flat space, in particular, holography, things holographically encoded at null infinity in the celestial sphere. You might even call it, I don't know, celestial holography or something like that. I'm not sure. Just throwing stuff out there. But let's start with just ADS CFT as we know and love. So in reality, ADS CFT was discovered by Juan thinking about d-branes and the low energy limit and the decoupling and so on. So it was sort of very much a top-down story coming from our understanding of string theory. But there's an alternative history where we could have discovered, I think, something like ADS CFT, or at least guessed at it from the bottom up, just by thinking about sort of the low energy limit of quantum gravity and asymptotically ADS spaces. So there's been various versions of this story told. I particularly like the one by Don Wolf. But I was going to start by telling a version of it. So it's going to be a version that's sort of in a modern language of von Neumann algebras and so on. So let's say we just start in anti-de Sitter space, and we're going to take, okay, we don't really understand how to do quantum gravity in anti-de Sitter space, even in the bulk, even with string theory. We certainly don't know how to do it if we didn't know about string theory. But what we could do is just take the limit where the coupling to gravity goes away, and then everything's pretty simple. Everything just becomes QFT, where by QFT I'm including some free gravitons propagating around in this fixed background. Okay, so that's all fine. But then we could notice something. We could ask about, if I just know about what's going on at some time slice of the boundary, if I can just see the observables at t equals 0 on the boundary, then I could ask, what could I know? Could I discover holography this way? So just because local operators aren't very well defined, and for future reference, I'm going to imagine instead asking a slight variant of this question. If I have some small neighborhood of a time slice at infinity, what can I learn from operators there? So what operators can we measure in this small region? Well, if we just had QFT, if we were really just doing QFT, all we could really measure would be some local fields phi sitting in this region, where phi includes like graviton operators and stuff. But we're not doing QFT, we're doing quantum gravity, even if we've taken G Newton to 0. And that gives us something that's sort of different and interesting, which is the ADM mass we can also measure in this region, right? So HADM, if we're just working perturbations of Minkowski space, then it's just an integral of the stress tensor. It's just the Hamiltonian of the QFT. But because we're doing quantum gravity, we have some sort of gravitational Gauss law, where it's also equal to, very schematically, some sort of limit as r goes to infinity of the sort of perturbation to the metric out at infinity. Yep. Let's, okay. All right. So HADM in this limit is just the integral. It's just the ordinary Hamiltonian of the QFT fields. But it can also be measured by measuring the metric of at infinity. Okay? And then the final thing that we can do is if we can measure these things. We can also measure any operators whose matrix elements we can approximate arbitrarily well with these things, because that's really what quantum measurements come down to. And so that means we should take the closure of these things under something called the weak operator topology, or equivalently, we should take what's called the double commutant. Okay, so this is where von Neumann algebras come in. It's because if we can approximate measurements, then we can do those measurements arbitrarily well. We can basically learn everything we could. And von Neumann algebras are super powerful because they let us do a couple of things that we otherwise couldn't do. The first is that if we can take sums and products of these things, and we can also take the double commutant, then we can do things like exponentiate operators. So if we can measure HADM, we can also measure e to the I HADMT. And so that means if we can measure phi and we can measure HADM, we could also measure phi evolved in time using this ADM Hamiltonian. So that means actually, even though we only thought we could measure stuff in this small neighborhood here, we can also measure time evolutions of this operator. So secretly, we've now discovered, I'm going to use blue for this, hopefully that's okay. It's just for sort of shading. We can actually measure stuff in this whole boundary at any time. This is something very non-trivial that we've learned because we've done quantum gravity. The other thing that double commutants let you do is it lets you use some powerful theorem from algebraic QFT called the time-lag tube theorem. And the time-lag tube theorem says that if I have some tube traveling in time, then I can actually, just by doing measurements on that tube, I can secretly measure any observable in a sort of causal diamond surrounding that tube. In this case, the tube goes from minus infinity to plus infinity. So that actually includes the whole space-time. So what we've learned is that this algebra, that's just stuff we can measure in this small neighborhood of this time slice, is actually the full algebra of all QFT operators within this asymptotically ADS spacetime. Okay? So I would want to call this, for want of a better word, perturbative holography. It's not the full power of ADS CFT. We haven't discovered n equals 4 super Yang-Mills as a description of this thing. But we've learned that in this G-Newton goes to zero limit, then observables here actually capture everything. And maybe if we'd really properly discovered this, there were certainly hints at it, but if we'd really realized it before Wundt's work, then maybe you might guess that actually this is the perturbative realization of a non-perturbative effect, and that there's some microscopic boundary theory out here, and then we could have tried to find it that way. I don't know if we'd have come up with any examples, but it would have been one approach we could have taken. Okay. So very quickly before I move on to flat space, we can also talk about the case where we don't just have empty ADS as our background, and instead have some black hole geometry. But otherwise, we just do exactly the same thing. We try to look at what we can measure near this neighborhood of a time slice at infinity. The story is essentially exactly the same. We again can exponentiate. That gives us this time sort of some tube going from minus infinity to plus infinity. And then we can do the time-lag tube theorem. But this time it doesn't give us the whole space-time. It just gives us the right exterior of the black hole. Okay, so we've discovered something else about holography. We've discovered some sort of notion of, I'll call it, causal wedge reconstruction. In fact, in this case, it's the whole entanglement wedge because the two are the same. Whoops. Well, that was great. But in general, we're not going to be able to get, in more complicated backgrounds, we're not going to get the whole entanglement wedge this way, but we can certainly get the causal wedge. And with a bit more work, we could get something called the simple wedge or the appetizer. That's something that was worked out in a paper I wrote with Netta and Arvin a while ago in different language. So we can learn quite a lot about holography without ever really doing anything except QFT. So this algebra, by the way, is this famous type 2 algebra, first introduced by Edward. I'll call it a black hole. So this is some type 2 von Neumann algebra. It has an entropy that is an entropy that includes the Bekenstein-Hawkey entropy of the black hole. All right. So we'd like to tell something like the same story in flat space. There's a couple of ways we could try to tell it. I think the easiest would be to work in a small neighborhood of spatial infinity in flat space. The story goes through quite nicely there. But the boring thing about spatial infinity is it's just one point in the compactification of flat space. So you have no notion of like holographic dynamics, right? Something very interesting about this is we can note that this algebra at t equals 0 is the same as the algebra at t equals 10. And that could give us a hint that there's some unitary time evolution going on in this boundary theory. Okay, so we want to have some notion of dynamics of different holographic algebras being related to each other in an interesting way. We're going to have to work at null infinity. So here's null infinity, and we're going to consider some cut that's described, I'll call it u0 of omega. Omega is the angular directions, u0 is just retarded time of this cut at future null infinity. And just like I did before, we're going to consider a small neighborhood of this cut. We're not just going to consider the cut itself. I'm going to be a bit more precise about this neighborhood than I was at ADS because it is going to be somewhat important. So I'm going to imagine this neighborhood is going to extend in to some radius that I'll call R0, and it's going to extend for some small interval delta u in advanced time. Okay, so you should imagine that eventually I'm taking the limit where R0 goes to infinity and delta u goes to 0, but we're going to keep them explicitly finite for now. So for each of those reasons, I'm going to construct an algebra that I'll call A u0 delta u R0. And then eventually I'm going to want to say that this sort of algebra associated with the cut itself, it's just going to be sort of the intersection of all these algebras. It's going to consist of things that you can measure for any R0 and any delta u, and in particular for arbitrarily large R0 and arbitrarily small delta u. Okay, great. So why am I putting in so much effort to be very explicit about the fact that we're going a bit away from this cut? It's for two reasons. Firstly, we want to be able to talk about massive fields. Okay, there is no good notion of a massive field operator at null infinity. Right here in this argument, it was important we sort of had all local fields in the bulk so that we could really apply time-leg cube. And so now that I've got a finite amount in, then I can just talk about local massive field operators. So y finite R0 There's a second reason that has to do with the equivalent of the ADM mass at asymptotic infinity. So the equivalent of the ADM mass, I think most of you will be aware, at least at a very surface level, is this thing called the Bondi mass. Okay, so I'll call that MB. And just like HADM, at a very schematic level, so this is labeled by some u0. This thing just looks like a limit as r goes to infinity of some function of the metric at r and u0 in different angular directions, integrating over angular directions, divided by g Newton and multiplied by r, right? The fields drop off as 1 over r, and the back reaction is order g Newton. So this is something we can locally measure, sort of out here on this cut. And it's equal by the constraints to the ADM mass, a spatial infinity somewhere deep down here, minus the energy of everything that's sort of already escaped the system before this time. So that's the integral over angular directions times the integral du from minus infinity to u0 of TUU. We just have to subtract off all the stuff that's already leaked out of the system. The trouble, of course, is that's all totally fine classically, but quantum mechanically, this is some nasty divergent thing. This is not some densely defined operator. And the easiest way to see this is, okay, at least in Minkowski space, this is just the integral of TUU over the whole. HADM is the integral of TUU over the whole of null infinity. Then we're subtracting off integral over half of it. So basically what this is trying to do is it's trying to take all fields above this cut and translate them while leaving all fields below this cut unchanged. That's obviously a bad thing to do. It's a totally singular thing, and so it's not going to be a good operator. Okay, good. So how does going to finite R star help? Well, what we can do is we can define some sort of regularized Bondi mass that I'll call MB tilde u0, which is defined as basically the Bondi mass, but at some finite radius R star. Okay, so this is very schematically H at u0 and R star over g Newton. And if we define it the right way, I'm not explaining the details of how, we can make it so that this is basically equal to HADM minus the constant time integral over R from R star to infinity of TTT. Or equivalently, so this is just the, like HADM, but cut off at some finite radius. This is the integral from 0 to R star dr and d omega of just the energy. This is just in the flat space case. Okay, this is just the gravitational Gauss law says that this integral is related to some function of the metric that I'm lazy to write down. Okay, just it's basically the Newtonian potential times R. Okay, great. So the important point for us, this thing is also not UV finite. It also has quantum divergences. But we can take this and we can smear it in time a little bit. We can keep fixed R and we can smear a little bit in U0. And then that becomes just this operator smeared out in time a bit. If we can exchange the integral in time with the integral over space. If we take the stress tensor and integrate it out a bit in time, that's actually a UV finite operator. All the divergences go away. Okay, so this is genuinely something that is in our algebra. So this algebra is going to include local fields sitting in this region, this regularized well-defined Bondi mass, and of course everything that's in the double commutative zone. Okay, so let's try to make a similar argument we made for ADS about what this gives us. So I'm going to do a slightly zoomed out picture now of Minkowski space. Okay, so we've taken g Newton to 0 again, so we're just working perturbations of Minkowski space. Okay, so let's choose some R star and consider MB of R star at some point here. And then I'm going to consider some operator phi that's localized within my region, but further in than r star. Okay? Now, the commutator of phi with HADM is just the time derivative of phi. This thing, that thing is not HADM, but it's HADM minus something sort of integrated from here to here. And phi is space-like separated from that part, so it commutes with that part. So the commutator of phi with this regularized bonding mass is also just the time derivative of phi. So we can use this to evolve phi forwards and backwards in time, except at some point we get a problem. At some point we're going to become light-like separated from this point. Then the commutators with this second term up there are going to become non-zero. And we're not just going to end up evolving phi in time anymore. Instead, we're going to do some sort of non-local nonsense. I don't know exactly what we'll end up with. Roughly, it's like you want to evolve these fields back in time, but not these fields back in time. It's a bit weird. It's just going to be something ugly. Okay, but we get some nice tube going from here to here. And then we can do our second trick of our two tricks. We can consider the time-like tube of these things, so that will give us some diamond that looks like this. But remember, we could have picked r star to be anything finite we want. We could have made it arbitrarily big. So let's make it really, really, really close here. Now, the diamond associated with this time-like tube is basically going to be this whole diamond like this. That's the second one I smashed. That's impressive. Okay, great. So this is pretty good. It's sort of similar to the tricks we pulled before. It's some region. But we can actually do better than that, because we now know that we have all operators within this region are actually in our algebra. So we can go back to our first trick and start evolving some of those operators in time. We can in particular take some operator sitting at r equals 0, and we can conjugate it with the exponential of e to the im v tilde star. It's space-like separated from all this stuff. So we can evolve it backwards in time and forwards in time. Forwards in time doesn't give us anything new. But backwards in time gives us new stuff all the way down to here. And then down here, it's going to start doing some weird non-local stuff. Okay, then we apply time-like tube for a second time to this whole tube going here. And now we get a much bigger region. We effectively get everything inside this cut of null infinity that we started with. Could we get any further? Well, no, we can't, because the set of operators that commute with this region are just radiation operators that escaped out here. Those commute with all our fields in this little region. They also commute with MV tilde star, right? Because MV tilde was just the integral from 0 to R0. It's just an integral over here. So these are actually genuinely in the commutant of our algebra. So the double commutant had better commute with all these things. And this is the largest algebra. This is the this is the commutant of these things. So that's everything we can get. Okay? So what we've learned is that for any choice of R and delta U, for any R and delta U, R0 and delta U, the algebra localized within this little region actually is just everything inside that cut. That means also the algebra of the cut itself, which we just defined as the intersection of these things, is exactly the same algebra. It's this whole thing inside. So this is sort of similar to what we had in ADS. We get a lot of the spacetime. It's not quite the same. It's not the same for two reasons. First is that previously in ADS, this was just the algebra of the entire spacetime. In flat space, it's not. It's just some type 3 algebra associated to the subregion. And the second point is that previously, we ended up with the same algebra for any cut. If we started at t equals 0, or we started at t equals 1, or anywhere else, we always ended up with the same algebra that was just all operators on the entire spacetime. In this case, we get something different. If we chose some second cut up here, U1, then the algebra associated with that is this red region. So we instead have the for U1 in the future of U0, some cut in the future of another cut, the algebra gets strictly smaller. So there's information leaking out of this system as we try to evolve along null infinity. What is that leaking information? It's exactly the radiation that escapes out the system between time U0 and time to U1. Okay, so I think this is the right story, that if we're going to have some version of holography in asymptotically flat spacetimes, this is what we should be looking for. We want to associate degrees of freedom to a sharp cut. They should be type 3, not type 1. And the evolution along null infinity needs to be irreversible. There should be a map from a state on U0 to a state on U1, but there should not be a map the other way. To go back the other way, you need not only the sort of holographic state on U1, you also need to know all the radiation that escaped out in between the two times. It is worth noting that because this is just QFT, we do have something called the split property. This says that given any U1 in the future of U0, we can find some algebra that I'll call A tilde that contains all operators in U1, so it contains everything in this red region. It is contained in this blue region, and this is actually type 1. So this is basically saying we can regularize these entropy divergences. These entropy divergences are just coming from the fact that there's this sharp edge of this cut, and there's radiation escaping out just before, and that has vacuum divergences. And if we just smear out the cut in time a bit, so we have just a U1 and U0, and we just need our algebra to be somewhere in between the two, we can regulate those entropies. Okay, great. So I have about 10 minutes left, which I think is just about the right of time to say the remaining thing I wanted to say, which is just to talk very briefly about black holes. So we already talked about that in asymptotically anti-de Sitter space. Take my jacket off, I apologize. Okay. So the story is going to go through in a pretty similar manner. Okay, so we again have a cut. We have a small neighborhood of that cut. And we just go through exactly the same set of steps. So we no longer, what changes in this equation? We no longer have this formula. Instead, we have something that says that MB tilde is very schematically equal to MB tilde minus some divergent constant is equal to whatever, T area of the black hole over 4G, like the irreducible mass of the black hole plus the energy of all fields outside the black hole, the boost energy, which is like in Schwarzschild coordinates, it's just TTT. And this is just an integral dr from r horizon to r star, and again, integrate over angular directions. This is only meant to be very, very schematic, but hopefully the interpretation of it is clear, even if I wrote down something totally wrong. This was supposed to be the energy of the black hole up to a constant, which is d equals TdS, so it should be right. We're considering small perturbations in the black hole, so everything's linearized. And then we have the energy of everything in between. Okay, great. So then trick 1 take a field inside this MV tilde. We'll take this very, very close to the edge. Take our field and evolve it forwards and backwards in time. Okay. Step 2, apply time-like tube theorem. Time-like tube about this, all fields flowed forwards and backwards in this region, gives us the diamond that I just filled in. Then, once we have this diamond, we then look for another point in the diamond and evolve that backwards in time. So we can make this very, very close to the horizon, evolve it backwards in time, gets all the way to here before it becomes time-like separated from the stuff that got subtracted from HADM. At that point, it would start doing something non-local that doesn't correctly do time evolution on these fields, which it's not commuting with. So we get exactly up to this point. We apply time-like tube to this nice tube here, and we get some region that looks like this. Okay, can we get any more of the black hole than this? No, that's because everything we've found so far, everything in this original region, commutes not only with these operators, radiation operators that escaped out here, but it also commutes with the left ADM mass over here. Right, it's just on the other side of the black hole. We're starting with operators dressed to the right boundary implicitly. And it commutes with matter operators off at the right boundary. And their double commutant includes all of the left exterior. Okay, so all of our operators here have to commute with everything in the left exterior dressed to the left boundary. And with all the radiation here, this is the full set of operators that do that. So we found everything that we used to found. Okay. So I want to claim that this is the entanglement wedge in this black hole background of the cut at U0. So this is sort of all the information that is holographically encoded in fields out near infinity at this cut. Okay. I think that's basically everything that I have to say. So I think I'll just give more time to questions. Okay, let me just make one final comment, actually, about the type of this algebra. So remember, in the ADS case, in empty ADS, we got a type 1 algebra, which is what it really is non-perturbatively. For the black hole background, which I think might have got erased by this point. Oh, no, it's under here. For the black hole background, we ended up with this algebra that was actually type 2. That has to do with the fact we took this G Newton goes to 0 limit, and that made the Bekenstein-Hawking entropy infinite. In the flat space case, here we got type 3, but with a split property giving us type 1. In this case, we're going to again get type 3 because we have this entanglement with radiation fields, and there's this vacuum entanglement here that is type 3. And if you have any type 3 entanglement, then it doesn't matter what other stuff you have, you're going to end up with a type 3 algebra. So this is still type 3. But now we have a claim. I'm not going to justify this, partly because of time and partly because I don't quite know how to do it, but I think it should be possible. That's why they call it work in progress. We have a split property that says if we take the black hole algebra some U1, right, that's still contained, strictly contained in the black hole algebra at U0, the U1 in the future of U0. They should have an algebra in between that sort of gets rid of this type 3 entanglement with the radiation. But it will still have type 2 entanglement across the black hole horizon. So this will be a type 2 algebra. And you could compute, I claim that you could compute the entropy of this algebra, and you'd see a term that looks like the Bekenstein-Hawking entropy that comes from the sort of type 2 entanglement across this horizon in the same way that it happens in the ADS case. So yeah, I think that's basically everything I have to say. I'm very interested in people's questions, so please do ask lots. Yeah.
So if there's a analog of HKLL reconstruction here, where would the sneering be? Over what?
Yeah, good. So let me tell this story in HKLL language. Right, so first what you do is a bulk to boundary propagator that gets you to this thing here, right? And then you know, that becomes boundary operator smeared and it's smeared over boundary time. And then the sort of holographic part, the non-trivial holographic part is not that, that works in QFT. It's the fact that you can then just do boundary time evolution to relate it to this point here. Okay, so my two moves were the time-like tube theorem and exponentiating with the Hamiltonian, evolving in time with the Hamiltonian. The first one is the HKLL one. The second one is like boundary time evolution. In this case, I did 2 of each type of move. I did, time evolution of this operator, then some HKLL-like thing to relate this operator to some integral over these operators, and then I did time evolution of this operator, and then HKLL-like thing to get all of this region. So if I had some arbitrary operator here, I'd have to first use HKLL to write it as some integral over this, then write that as conjugations of the Hamiltonian over here with this operator, and then write this operator in terms of these, and then, yeah. So it's a somewhat complicated process, but it could be done.
Yeah, so this thing you're calling evolution on future null infinity, I mean, future null infinity is really Cauchy splice. So I think it's more like tracing out than it is like evolving. You're just talking about the state.
Yeah.
So to have a theory, what you need is something to go from scribe minus to scribe plus. So
yes.
So are we just doing kinematics, or what are we doing here?
Yeah, probably the interesting part is in the S matrix. It's not a trivial tracing out because I've not written because holography lets me write everything in terms of degrees of freedom written here. You know, it's not like I just wrote it as some degrees of freedom over all of scribe plus, and then and then just like traced out over them, right? There's some undoing of the holographic map going on as you turn some of these into just radiation degrees of freedom, and then end up with whatever holographic thing you had before. Whether that is trivial and whether that's non-trivial and interesting, or whether whatever kinematic way of writing this holographic state, if there even is one, just makes it obvious how to do that, and all the interesting stuff is in the S matrix, I don't know. I'm not going to question you if you want to say that, yeah, the S matrix is all the interesting stuff. And
value judgment, I'm just trying to understand.
Yeah, so okay, in ADS, you could ask, like just on a time slice, if I have the CFT state at infinity, how do I sort of move into the bulk, right? And how do I then decode the bulk from that? How do I do the bulk to boundary map? So maybe you can think of what I called evolution as instead undoing the bulk to boundary map. So you have some boundary state here, and then you undo it into like a partial bulk state plus a boundary state, and then go on. It's sort of halfway between the two, because null surface is halfway between a space-like thing and a time-like thing. Yeah.
Just wondering, in that example, it looked like you really used the Schwarzschild time to go back in a way that, like, if, for example, if the black hole was something fell into the black hole of some order 1 deviation from exact Schwarzschild, would there be a picture like that?
What do you mean by order 1? You mean some like quantum field, like a few particles, or like some big classical?
Big classical.
Classical back reaction. So order 1 back reaction. Yeah. I think it still works. I think you can do it. I don't want to assert that's too strong right now. I again will appeal to these 3 letters I wrote at the beginning that let me get out of any jail free. Yeah.
Too many. Go ahead. I'll just move this way.
So I sort of have 2 related questions. In the past, people tried to make sense of taking a zero curvature limit of ADS. You might answer that that's just the wrong order of limits or something, but part of the reason I'm asking is you have this R naught in order to accommodate massive fields and to not be quite talking about null infinity. So because of that, I wonder if they're
I think the difference with taking like a flat space limit of ADS is you have all this rest of ADS outside it, and you're naturally, so I guess you have sort of, some little flat bit in the middle that's actually really big, but never mind. But then the sort of fundamental variables you're wanting to talk about are like stuff down here and stuff up here. Whereas here, I'm really zooming in on the stuff here. Does that make sense? You can say they're maybe not too different, but yeah, maybe they're not too different. I'm not claiming they are. Just
in the ADS case, the two moves somehow you mentioned we get the causal wedge, but in this case you're claiming it's the entanglement wedge. Are we missing
just
something?
in this simple case, I think the two are the same. Because we have complementarity, the two are the same. So we
Like the claim is about the causal wedge, and in this case, it's done.
the claim is, I think you can probably, if you really worked on it, get the simple wedge, so to the outermost extremal surface by these sort of moves, and slightly more complicated versions of them. Yeah, in this case, there's no like Python's lunch or anything, so that is the entanglement wedge.
In the example of an evaporating black hole in flat space, what happens to your algebras after the Spacetime?
Yeah, so we've taken G Newton goes to 0, so we're not seeing any of that. Of course, I would like to I would hope that just like this perturbatively holography could have led us to guess about non-perturbative holography, then something similar would happen. And yeah, so I would want to say that this is, okay, so Suvrat likes to say that there's no page curve in flat space. I want to say this is the thing that obeys the page curve. I think he would agree with that being a thing that obeys the page curve. I've had conversations to that effect. But yes, so I want to say that this algebra, these two things are hopefully well-defined non-perturbatively. I say that without evidence, but if you go far enough away, there really is just free fields. Of course, there's a trade-off where we needed to not go infinitely far away, but I think you can probably squeeze that through somehow if you really understood what you were doing. So I do think the structure is maintained, but I'm not asserting that I know how to show that.
Geoff, as much as I agree with the spirit of what you're doing, there is a problem with trick 2 at the order of perturbation theory that you're working in. At the order of perturbation theory that you said at the beginning, HADM is not an operator, so you can't exponentiate it. If you include the constraint in the bulk, you can, but that constraint isn't a constraint until you go to the next order of perturbation theory.
And I think we can talk about this offline, but I think there is a consistent set of things I'm including and not including. I'm treating the second order variation in the metric as an operator valued thing that is just determined by the constraints. I think there's a consistent way to do this. Yeah, like the paper I had in January on graviton entanglement entropy, I think we were somewhat clearer about it there certainly than I have been in this talk. Yeah. There's no new degrees of freedom at G2, so it is just operators acting on the same things that we had already. Yeah.
Do you have a version of the generalize the second law in the setup? I guess as long as you have this kind of like split, you should have an operator valued weight from the bigger algebra to the smaller one. So I think maybe you can prove some kind of generalized second law based on this.
Yeah, I think the generalized second law, okay, this algebra is too big to just know about the causal wedge at some time because it's able to see all the way down to here. That's basically because it has the Hamiltonian in there, and that gives you too much. I think, personally, I'm not satisfied by the second laws that we've been able to derive using sort of algebraic methods. We can maybe talk about why offline, but roughly, yeah, if you're going to say that you have a second law associated, some smaller entropy associated to an algebra sort of on this region, then that algebra should be included in the algebra of this bigger region. And if it isn't, you're not really talking about the algebra of this region. I think the only example where that has been done was in a very special case in my paper with Edward and Ben, where we consider the black holes that is allowed to equilibrate for a very long time. And then there, in ADS, at least, there is some algebra. I haven't thought about how that would work in flat space. yeah, I can make more detailed comments about it, but I don't want to be a distraction.
What precisely is the nature of the non-local phenomenon behind the cut?
It's not, so, I mean, just think about Minkowski space. Let's say you have the integral over t in some little diamond, and you like integrated this a bit over time, so it's well defined. Then you take some phi in the middle of the diamond, and you conjugate that. You'll have some flow that looks normal until you hit here, and then it will just, it's just like taking, if I conjugate operator by the exponential of some other random operator, in general, there's not going to be a simple way of writing that down beyond just the thing you get by that conjugation. It's really only in very special cases where the larger operator is either a symmetry generator you'd expect to be local. This isn't a symmetry generator, but it's the Hamiltonian minus something that's space-like from this. So you can pretend it's a symmetry generator until you can't anymore, and then yeah, the magic stops.
Yeah, in your paper with Chang Han on there's a section on general extreme bounded by general extremal surfaces and how you could get a type 2 algebra. This blue region is bounded by an extremal surface. So why do you not want to say it's a type 2 algebra in this case?
I think in that case we basically ignored infinity. Yeah, like I think we basically assumed we had a compact region bounded by extremal surfaces. You just have this entanglement of radiation modes, like just out near. It's all coming from this stuff out near asymptotic infinity, where it's really just like free fields, and there's free fields going out across a cut, and that gives type 3. It's all from that, yes. So that's why I said this thing about you have a type 2 split property thing, right? Where if you just smear out this cut a bit, that's just like killing off that divergence out here. It's not doing anything to the entanglement here. I think that should be enough to make it type 2.
If I understood correctly, the difference, one basic difference between the two cases is that in the flat-space case, you have to include a finite region as a starting point. And so I guess in the EDS case, in this like bottom-up way of getting holography, you can think of this arbitrarily small slice as maybe telling you that there is a codimension 1 theory, which is dual. Can you say something about what this is suggesting for the dual of flat space? Does it mean there's a codimension 0 or?
Yeah. So, okay, at some level, I do agree. You definitely can't just do it a single time slice because there's no, to get well-defined operators, you need to be able to smear them out in time in general. So you definitely want to talk about some little interval at infinity. But I agree that in ADS, you can sort of rigorously define limits of all the operators you care about and avoid going into the bulk a little bit. I'm not certain if that's just a technical oddity or something deeper. Yeah.
So the evolution from the smaller diamond to the bigger one, you do in the third step.
Yep.
From the point of view of the quantum field theory, in order to do that, you need to know the state at the horizon of the black hole. So does that mean that there's some something that? Like,
yeah. So I think the point is that you have the Hamiltonian, and yeah, that's enough. So you can write this thing as h left minus an integral over all this stuff. So it doesn't commute with the things here. So you know about that because gravity, everything has to sort of be gravitationally dressed, and it knows about it. I agree it's a bit odd, and you can convince yourself it shouldn't be possible, and then you think about it more, and at least if you convince yourself it's all fine. Your mileage may vary, but no, I'm pretty sure it just, the Hamiltonian knows about it. The QFT doesn't, but the Hamiltonian does.
Can you comment a little bit more on what properties of the split inclusion carry over when you have a type 2 algebra sandwich rather than type 1?
Not really, because I don't know much about it at all. This is a thing we thought about in the last couple of days, and I don't think any of us have got around to trying to understand the literature on it all, or whether anyone's thought about this.
retain some of the same properties in the.
What ones are you thinking of?
Sorry?
What properties are you thinking of?
Like, well, for instance, like the existence of an operator value in weight.
Yeah, that's a good question. I don't know. I would have to think about it.
Okay, last two questions. So in ADS, there are these, in classical gravity, there would be some kind of gluing theorems that I would be worried about. If you give me, space-time data, if you tell me the metric in some neighborhood of the boundary, but there are various solutions I could glue into the interior classically. So I guess could you comment on what feature of quantum gravity is allowing us to evade what would seemingly be,
Quantum mechanics is far more analytic than classical mechanics. That's why you have things like time-lag tube theorem and stuff like that. Or well, sorry, it's not having the time-lag tube theorem. It's the fact that time evolution is analytic. Yeah, like classically, it's still true that if you have all of this data, then you have uniqueness theorems that say that fixes everything everywhere, at least in the the linear setting. But yeah, quantum mechanically, classically, there's a beautiful paper by Ted actually pointing out why sort of the classical version of this argument doesn't work. You might think, you have the data sort of here, and you have the Hamiltonian. You can take Poisson brackets of the two, and so you should be able to work out what's happening up here. But it's just not true, because the sort of Poisson flow can be non-analytic. You can have some bump function here. There can be no sign of it whatsoever, and all the derivatives here, and in the Hamiltonian and everything else, and then it just comes out and still hits you in the face when you're least expecting it. Quantum mechanics, you can't have that, because you have these properties of von Neumann algebras that you can exponentiate things. If you have the operator, you have the exponential of the operator.
My question was whether it's possible with your two steps to see like a causal wedge for finite boundary subregions.
A finite boundary subregion, you mean like in ADS? You mean like part of the boundary? Like half of the boundary or something? Yes, I think you could do it, just use the Windler Hamiltonian instead in this case. I think this is something I didn't say, but I think it's true. If you just took like half the boundary or something in this case, I think it doesn't have any non-trivial sort of causal wedge equivalent that you can get. But also, it seems to not have complementary recovery. So at the perturbative level, there's like a gap between the equivalents of the causal wedges. Maybe there are entanglement wedges that are bigger and do have complementary recovery. Maybe there just aren't complementary entanglement wedges. That's a weird magical property of ADS CFT that doesn't have to be true.
Okay, I think with that, let's thank Geoff.